afternoon. My name is Audrey. I'm process engineer in Fluid Air, and it's a pleasure for me to present you an innovative spread dryer for thermosensitive microorganisms. Before to start a short presentation about Fluid Air. Fluid Air, it's a division of Spraying System. It's an American company, manufacture nozzle, and Fluid Air is specialized in solid dosage equipment like fluidized bed process, fluid bed beds, high granulation, size reduction, mean milling, and we do by yourself the process automatization, and the last one but not the least, the electrostatic spread dryer, the technology that I will present you today. Today in the market, in industrial scale, you have two main drying. The first one is the freeze drying. So the freeze drying is great because you work at low temperature when you want to dry thermosensitive compound. It's good. You have in this case high yield, but you obtain a cake. So this cake you have to mill. So that means that you have to add another process in the loop. It's a batch process, and also you have to use time and energy to dry, a lot of time and energy. In another part, if you want to work continuously, you have the conventional spread dryer. It's great because it's a large scale equipment. So for example, in Austria you have a really big installation to have a milk powder, but as main disadvantage is to have to use high temperature to evaporate water, solvent in general. And the particle size that you obtain, it's really small. You are fine below 5 micron. So you need to, after, to use a fluidized bed to granulate. So it seems that we have something missing in the middle, and something should be great to work with lower temperatures than the conventional spread dryer. That means between 30 to 100 degrees C, and also like that to have high preservation of thermosensitive compound, to work continuously, and to have easily scale up between the laboratory to the large scale. So it's when with this remark that we decide to develop electrostatic spread dryer that I will present now. Between electrostatic spread dryer, what is electrostatic spread dryer to start? So the first time that I heard this name 3 years ago, in my head it was something like that. Sorry. So with some flash and but in reality it's not like this. It's less noisy. So we use it look like a conventional spread that we say now, conventional spread dryer. So we have a nozzle and we atomize droplets that is dry. We use nitrogen gas to dry it. It's come at the bottom, and it's a BPI nozzle where we apply an electrostatic charge. So now, what is the difference between the conventional spread drying and the electrostatic spread drying? So in case of electrostatic spread drying, so it's that, you know, we can say it's free water. When you have free water, it's really easy to evaporate the water, but at one point your water stay in the middle, and at the same time your carrier or your active, you have it's start to dry, and you have a creation of the crunchy shell, and after that you have to evaporate your water from the center to outside and pass through the crunchy shell. So for that you have to apply a really high energy. That's why you have to increase your temperature. And in this case, when you have thermosensitive compound, you damage it. In case of electrostatic spread dryer, what's happened? During the when we apply a charge, we help the water to diffuse really well in the droplets, and like that we don't keep water in the middle. We help the water to move at the surface like that. So that means we don't need to have a high energy to evaporate it. And moreover, you create a thin layer of water around, and like that you can protect your active or during the drying. So that is something new. It's the most important parameter now. It's not the inlet temperature, but it's the outlet temperature and how to manage the outlet temperature to assure a good drying of thermosensitive compound. In the case or you have different compound inside, if we can take the case of emulsion, you want to dry oil, so we can say that oil is the drying here. Your active is oil. You have carrier here and with water. So in conventional spray dryer, when you will evaporate water with high energy again, with high heating, you will have an homogeneous repetition of your oil and your carrier. So that means that you have oil at the surface, and this oil could be damaged by oxygen, and also in case of essential oil will be evaporated during the storage. In case of the electrostatic charge, we apply a charge and it's helped to do a stratification of the compound in function of the polarity. So we use a solvent, a polar solvent, and after we choose the carrier to have a polarity between the active and the solvent, and like that with the stratification of the compound we obtain really a perfect microencapsulation, because all the active compound is inside and you have something like a coating around your active, and you don't have oil at the surface, so you have a really great encapsulation. At the same time, you product the temperature of the product, it's between 30 degrees to 80 degrees, and the moisture content, it's really below 1 to 5%. It's really depend of the carrier and the active. So the applications that we can have really short to we can say nutraceutical food application. We have essential oil, fish oil, also all carotenoids come from macroalgae, for example. We also some for colors. The fact that we don't create a crunchy shell to compare with a spray dryer. The porosity it's a little bit different, and the quality of the powder, it's the porosity and the quality is different, and we obtain a really great powder with a high flowability, and with we can say less oil at the surface or less hygroscopic. So that means that it could be also using to functional powder for food. If we come back more on pharmaceutical application, if we want to go tablets, that I say we have a good flowability, and we change also the density, so we can go directly to the direct compression. We have also some application with virus and also with bacteria. It's a really great application that I will show you with probiotics. And of course, it's a new technology, and I know that you have also new products, so it could be a technology using for your future product. So drying probiotics, it's a little bit challenging. So why we want to dry? It's to increase the stability of probiotics. But the main point is to obtain powder. The second point is to have an active water activity below 0.3, and we have to avoid all inactivation that we can have with probiotics and bacteria in general, and also to assure a good hydration of powder when we want to reconstitute it. So what's happened when we want to dry? You can have dehydration, thermal, oxidative, and chemical inactivation. So you have to really be careful when you want to dry to avoid all of this inactivation. So in case of the freeze drying, I just wanted to show you a little bit more focus on probiotics. So you start at atmospheric pressure and temperature, and your first step is to freeze until minus 40, 50 degrees C. After that, you reduce your pressure and you heat to atmospheric temperature. In general, you avoid to have so many damage on your probiotics. In general, it's a process that you use when you have a thermosensitive compound. But in fact, you can have some damage due to the fact that you change the physical states of membrane lipid or you change the structure of the sensitive protein. So it's great, but it could be also optimized. In case of the spray drying, so the main issue with the spray drying is the fact that you increase your temperature below 100 degrees C and most of the time maybe higher. So in this case, you have thermal inactivation, and also you can have hydration inactivation. You need to find a compromise in the case of conventional spray dryer between the fast that you have to dry faster to decrease your hydration inactivation and don't go too higher on your temperature. That's why we think that we have an interest to use an electrostatic spray dryer because it's a spray dryer, so that means that we can dry fast. So decrease hydration inactivation, and at the same time we don't go too far in to increase the temperature, so we can avoid to have a thermal inactivation. So it's really interesting. To continue to be far away and to optimize the process for freeze drying and spray drying, most of the time it's interesting to use protective agents. Most of the time we use sugar. Why the most using and that we will use in this study, it's trehalose. In this case, we just have to be careful when we use a spray drying to don't be in a glass transition phase, to don't have something like a rubber in the tower, very difficult to dry, and you don't obtain powder, you just have something like a chewing gum. So that is also interesting with the trehalose, and we'll come back after on that. It's the fact that it stabilizes membrane and protein by replacing the water around polar residue within the macromolecular structure. So we will come back on this point. So the only point that we have to check with the electrostatic spray dryer, it's the electrostatic effect on the bacteria. It's kill it. It's something like help to stress the probiotics or not. So for this example, we decide to have Lactobacillus plantarum and Lactobacillus casei. We cultivate that ICU, we use trehalose. We compare freeze drying and electrostatic spray dryer. Be careful to work with inlet temperature at 90 degrees C and outlet temperature at 37 degrees C. To have a good comparison, we did some literature research, and with Cavalos in freeze drying using a freeze drying process and using trehalose, we observe that they have a loss of -3 logs in 6 months during a stability at 20 degrees C. In case of the spray drying process, so it's also interesting to compare with outlet temperature at 70 degrees C. After 100 days at 25 degrees, they lost 6 logs, so it's a bit a lot. Again, Perdana shows that we have to be really careful working with the glass transition when we use the sucrose. We have we can't be higher than in this case 75 degrees C after you have a thermal inactivation. Sorry. And at the same time, we don't have to be in this part to avoid to be in the glass transition. So it's very difficult to find the good temperature, lower to be not in this inactivative temperature and in this part, and at the same time helping to evaporate water and to reduce the moisture content. So that we want we really think that electrostatic charge help to give the energy that we can give by the temperature. So the result, so we compare the freeze drying and the electrostatic spray dryers viability and stability for 6 months at 25 degrees C. With the freeze dryer, we have a loss of 1.2 logs and electrostatic spray dryer 1 log. Just to remember you, 6 logs for after 100 days for spray drying. So that means that we have a really great result with the electrostatic spray dryer. And just to be a bit more fast, really high viability and stability in the storage at 37 degrees C to compare with the freeze drying. We did exactly the same study with Lactobacillus casei and with the spray dryer. In this case, it was the inlet temperature at 70 degrees C, and so that means the outlet was between 30-40 degrees C, I think. And we observe after 6 months with Turalose a loss of 1.5, and at 37 degrees C after 2 months a loss of 0.9 log. When we compare with the results that we have, so when you can see the curve, we can say the curve, the stability, it's the same for freeze drying and electrostatic spray dryer. We are really close in the case of 8 weeks with the spray dryer, but a little bit higher. A little bit higher than a spray dryer in case of 6 months. We think that the fact to use an electrostatic spray dryer, we have a more perfect microencapsulation. That's why we have it's really helped to have a high shelf life to compare to a spray dryer, and we have the same results as the freeze dryer in the case of Lactobacillus casei. So that means that we have the same viability and stability or higher than a freeze dryer. The fact to work at lower temperature using nitrogen, we avoid oxidative and thermal inactivation. We use also fast drying, so reduce dehydration inactivation. And the fact to use electrostatic charge, we don't kill the bacteria, the probiotics. And moreover, it seems that when we check the literature for example, Vanessens team in Netherlands, it seems that the fact when we use a Trehalose, it's helped to increase the intra-Trehalose content to compare without charge. Just a short point, production cost of electrostatic spray dryer, it's 4 times lower than freeze dryer. Just to conclude, so we have an electrostatic effect, and like that we can work at lower temperature. The fact to work with a stratification of the compound, we have a superior microencapsulation. We can also play with electrostatic charge to have granulation. All is in one product. It's a continuous process, and we have also recirculation of nitrogen to avoid to use too much. And it's very scalable. The model 0.1 that you can see here. Sorry, here, and this one is the model 50, and we go up to the model 200. So thank you for your attention. If you want more information, we have the website, and you can send us also some email. Thank you so much. Have a nice trade show.